okay, I will try. I will switch to English now. You have probably seen this. I don't presume pretty much any knowledge of any deep stuff. And actually, the more you're used to doing things in a certain way, this can actually be a bit of an asset. Not an asset, sorry, a liability, okay? So in a certain sense, those who haven't seen any set theory or logic, or who don't have a lot of experience proving stuff, might have an easier, it might be easier to get used to this way of thinking or seeing things. But the point is, you should always try to engage in a fight, a mathematical fight with all these ideas, and hopefully we'll get to find out some interesting stuff. There is a bit of chaos here, and I will try to map this chaos. So there are like, okay, the principal things that we will see are like, have to do with foundations of mathematics. So a reasonable question is, what do we mean by foundations? Can you see this? By the way, is it too small? Is it okay? Yeah? Okay. So, a reasonable question is, what do we mean by foundations? And the other crucial part is formalization. So, by foundations, the idea is we want something on which we can build the things that are of interest to us. Being like mathematicians or whatever we are, the idea is that I want something which permits me within it, I can define the things that are of interest, and I can do the things that are of interest. And usually doing things here means proving propositions that I want to convince my colleagues that are valid or stuff like that. So usually if you ask, like you pick a random mathematician today and you ask on what foundations are you working, probably the honest answer is I don't care. And maybe they've heard of something called ZFC, and they will say, okay, everything I do is actually formalized, is founded upon ZFC. This stands for Zermelo, Frenkel, and there's no third guy there, okay, it's with choice. There's a bit of inconsistency in the initials there. And it's kind of funny, if you walk around geography, you will see there are a lot of fanatics of this theory. But the idea is that we should not presuppose that foundation means this. So the first question is what we expect from this, from a foundation, let's say like that, let's say it like that. And the whole point of this course is to try to do mathematics in a way that doesn't presuppose certain established things. Pretty much the person to blame for these established things is one of the greatest mathematicians called Hilbert. And we are going to actually start paying more attention to one of his students that started getting into some fights with Hilbert. The student is Brouwer. And we will see some ideas then that have to do with, okay, so we have a lot of things that I will start writing down, and eventually I hope that they will make some sense. So we have some, maybe I should write some names here, so I will start with Brouwer. Brouwer, okay, I cannot write well for some reason, I will get used to it. And some ideas from proof theory. I will write the name of Gensen here. And more or less, what I'm trying to, what I will try to do here is be like those guys that knock on your door and say you have a minute to hear the word of our Lord and Savior, but it's not actually a Lord and Savior. There are many, and it's actually called Trinitarianism, Trinity something, has to do something with the Holy Trinity. So I will start drawing the points of this Holy Trinity. We have type theory here, and let's say this is the computation part, so we also have programming. And we have things like the lambda calculus, if you have heard about it. If not, it's fine. So this would be like the computational point of the triangle that I'm trying to design here. And then we have things like category theory and algebra and spaces, whatever that means. Maybe I should write topology and some order theory. order theory, and maybe topology. And the third part has to do with logic and foundations and mathematical logic and all the stuff. Principally, we have proof theory. And I will write logic here, which is a very broad term. So, yeah, the idea is that we have this trinity here, and pretty much the interesting concepts you will find here, they also have a corresponding concept here and a corresponding concept here. And the idea is that if you want to claim that you really understand any of those 3 points that let's say you discover a thing here, the moment you manage to understand how it manifests itself here and how it manifests itself here, this is the moment that you say, okay, I completely understand this point, and if it happens to be a new point, then you've made some like progress, an intellectual progress for humanity or whatever you want to call it. So we will study mostly, okay, obviously, type theory. Not so much of programming, but we will do some programming, so I hope you are not allergic to it. We will see some things of lambda calculus. Definitely, we will have like a crash baby course in category theory, because I know that it's not offered as at least not as an undergraduate course. So, okay, anybody had a course in category theory? I mean a course, not an interest, and I studied some stuff. Was it called category theory? Okay, so it's not really a course on category theory, but there are some categories involved. Okay, and it's an undergraduate course, right? Okay. About algebra and topology, we will mention a few things. I will mostly use it as an example. I will need some examples from algebra and analysis, and I think I can count on you that you are familiar with those examples, and if you are not, you can just skip this example and hope that the next will catch with you in some sense. Or you can actually ask, and we can elaborate these things. And even if you've seen some things, probably I will define them in a very different way, seemingly. Or maybe you will say, okay, these are equivalent, so I don't care. We will spend a great time, about 1 semester, trying to maybe realize or to convince you that when we say these things are the same, there are like different levels of how much we have the right to say that. And if we have like 2 equivalent definitions, it may make a difference if we choose one or the other, although some people will say they are equivalent, so pick whatever you want and don't worry about it. We will worry about it. So this is something that will bother us a lot. And we will see some things about order theory for the same reason that I mentioned. We will see some things of category theory. Anybody had a course on order theory? 0, okay, so this will be more exciting. So obviously we have only 4 hours, like 90 minutes. I have a surprise. I don't know if it's a good time to say the surprise. No, in a bit. So we have 90 minutes for like 2 times per week, and we don't have enough time to cover each and everything that I have here. But like how far we will go in each will depend on you. So like, okay, I just noticed that, is it some or is it only one who has taken a course in category theory? 2. A course? 3, 4. Okay, come on. Don't be shy. Okay. And who has studied category theory for the fun of it? Not necessarily, okay, some. Okay, so those who have taken it as a course didn't study it. That's cool. Okay. Okay. So about order theory, same question. Has anybody studied order theory or one? Okay. So for example, maybe it will make sense that when we start studying order theory, we'll go a bit further. Maybe you like it, maybe you don't. And then, like, I don't think we will go far with algebra or topology. There are other courses established here that will go far in these directions. How about proof theory? Okay, perfect. Perfect means almost no one. And logic, okay, logic is a very broad term. Traditionally, there were like 4 pillars of logic, which was like set theory, model theory, proof theory, and theory of recursive functions. This is kind of changing over the last decades. So when I wrote logic here, I don't mean like the course you will typically see if you take a course called mathematical logic. It's like just keep in mind that this point here has to do with logic or meta-mathematics or foundations or whatever that means. Okay, so I want to emphasize something here because you will hear this a lot of times, like ZFC is the foundation of mathematics. Okay, first of all, it's a foundations for mathematics, and there are tons of variations. It doesn't make sense to say, oh, I'm using set theory. Actually, I have to tell you which version of set theory, there are many, and which subversion of set theory, again, there are many. And it's not really honest, because actually when people say that I'm using set theory as a foundation for mathematics, it's not by itself, because by itself it cannot prove anything. So it gives you means to define and construct certain things that you want to define, like let's say you're doing group theory, and every time you will say this is a group, this will be translated to it's some kind of set with some properties, and every time you prove something, like there's an infinite number of primes, this ends up being like a statement about sets, because you want to translate everything as being just a set. But you cannot prove anything if you only have set theory, so this actually comes together with usually first order logic, which actually is the means to how you can prove things. So you have these axioms here, which can vary, as I said, pretty much say what you assume about your world of the universe of sets. And here you have like how you can infer new truths from truths that you have, a way to prove things. Don't wait for me to ask you if you have any questions. Just raise your hand if I say something you don't understand. Whether it's a word you're not sure how I'm using it, I want you to just ask, because I will not use fancy words just to sound fancy, okay? So if I use a word and you're not sure what it means in the context I'm using it, just ask, okay? Okay. Okay, so what we are going to do is we're going to see like a different idea of how we can found mathematics, and this starts a bit of history here. This starts actually with the first problems that we realized we need to have some solid foundations, and it doesn't make sense to start saying, oh, this feels right, it's a theorem, this doesn't feel right, it's not a valid proof. And it happens actually, I think a milestone there is Russell, which is a very interesting human being. And I suppose that everybody has heard the Russell's paradox. Anybody who has not heard of the paradox of Russell? Nobody wants to admit that, okay. It's fine, maybe you know some kind of metaphor about it, like a library paradox, or I don't know, the barber, or something like that, which is not very fair to call these things paradox, but about Russell, it is very fair to call it a paradox. So the idea is, I will not get into the details of the Russell paradox here, but the idea is that at some point, people were starting to build things on top of set theory. Cantor was studying some very nice things from analysis. This led Cantor to discover things about sets and actually put the idea of a set on the table, mathematical table, to actually become an object of study and not just a vague idea of a collection of some things. And at some point, Frege was trying to formalize and do some foundational work on which all mathematical knowledge would be interpreted and this kind of stuff. And Russell sends a letter to Frege and says, okay, I have a great stuff you're doing, but I have like a small objection about this point. And this was a very serious point. So people started, and pretty much everything collapsed. And this point, you want to have people that will step up and say, okay, I have an idea, I can save this. And the first person who does this is Russell, actually. And there starts type theory. So this is quite important for us in this course. So it starts with what Russell called the ramified theory of types. And On the other hand, okay, so what's the problem with it? Because there's a problem, and why are we studying if there's a problem with it? It's kind of too complicated. And in order to become a foundation, you need to actually convince mathematicians about it. And this very primitive and first version of Russell's type theory is quite heavy, quite, I don't want to use the word primitive, but let's say it's complicated. And at some point, Zermelo has this idea that, okay, we can use sets and logic as a foundations, and starts giving some axioms about what Zermelo thinks everybody should accept about the idea that mathematicians have of sets. But there's a very different flavor in the word axioms. Maybe I will use something like axiom versus versus law. So let's say you take a course on group theory. Who has seen groups? Okay, half of you are asleep. Okay, I think more have seen groups. Okay, usually when you see like a course on group theory, you start with a definition and you have some things that interchangeably you can call them axiom or laws, like the group laws or the group axioms, and pretty much you say, okay, like one of them will say I have an operation that is associative, and some others. And it's not like the group theory tells you that all operations are associative, right? And you're pretty used to that because you say, okay, what if this operation is not associative and it's a binary operation and I have a set and I have defined this on it? I have found a problem with group theory. No, it just means that the set you are studying together with this operation doesn't have the right to be called a group. That's it, okay? So we see this, this thing as a kind of specification. This word is not so common among mathematicians. And I can say that this particular group that you want is actually an implementation of this specification in the sense that it has all the things the specification asks, and it satisfies all the things that the specification asks to be satisfied as well. What was I writing? Implementation. Okay, and this is not usually how people treat the axioms of Zermelo. They pretty much treat it as, okay, let me see if I agree that these things are valid of what I believe in my mathematical heart about sets. So, for example, one of the axioms of Zermelo says that there is a set without elements. Okay, so the attitude that we have when we read this thing usually is not the same with a group theory axiom. We say, okay, let me see if I agree with this or not. While when you're reading the group axiom, you don't say, let me see if I agree that binary operations are associative. Okay, but if you actually want to study set theory and understand how things work and not have tons of surprises, you actually need to treat set theory the same way you treat group theory. There is an inconsistency in the naming, which is the following. Things that satisfy group theory axioms are called groups. Things that satisfy set theory axioms are not the sets. It's the things we call like universe of sets. So if you write this axiom like in set theory, you might have something like this. For each, I will start writing some logic formulas, let's say. For each x, there exists a y such that blah, blah, blah. This is an axiom of set theory. I don't know what I wrote there. You are like saying, my world of sets, my universe of sets, satisfies certain things. One of them is this. For each element of my universe, each member of my universe, there exists another member of my universe, and blah, blah, blah. And how do you call these members? You call them sets. Well, in group theory, you might see a similar axiom, like for each x, there exists an x prime, such blah, blah. But actually, how do you call the universe there? You call it a group. And how do you call the member on which these quantifiers quantify over? You call them members of a group. So there is a big inconsistency there between these two names. Like in group theory, the things that the axioms refer to are not groups, are members of groups. While in set theory, the things, like set theory takes its name of the inhabitants of its universe, while group theory takes its name of the various universes that we have. So this is a kind of important distinction. Unfortunately, we will not change it. I would like to change this and call this like universes theory, maybe, set-theoretic universes theory. Nobody will like this. But anyway, it's how things are. And if you keep this in mind, you will, a lot of things, actually, if you don't keep this in mind, some theorems will seem completely crazy the more you get into set theory. Because it will seem that you should have like the power set, which is like all subset of something, and there will be some subsets missing, and then you will start wondering, okay, how can they be missing? It's just a sub-collection. And you will find out that there's some like of bijection between two sets that should not have a bijection between them, and some crazy stuff. And the moment you realize that, okay, these axioms work like that, like group theory, and they're not like absolute truths that Zermelo decided to impose upon us, then you start treating set theory in the same way you treat group theory, and you kind of understand the idea better. Does that make sense? Is it okay? Good. Okay. I have like some keywords like axiom versus law, implementation, not exactly versus, but there are like some correlated keywords. And by the end of this course, the idea is that the cover, the first page here, will be full of these keywords, and I hope that the main point of this course is that we understand all those keywords. Okay? And it will not happen like if we start discussing here what exactly it means implementation, specification, or what it means for two things to be intentionally equal or extensionally equal. Or for those who have seen some programming, what it means to have like a static typing system, or what some people call dynamic types. I will give a spoiler here. So this is like type theory, and this is like set theory. So yeah, the idea is that we will learn this thing a bit by osmosis. By doing these things, we will eventually capture these ideas. Any questions? I will come back to this first page to add stuff to it. So now I will want to start with some notation. And the first one actually has to do with what I just said about intension and extension. And I will use this symbol to mean that these two guys, let's say if I write U and V, this means that U and V are equal, as we say. And this kind of means that they refer to the same thing. So if I understand what U is saying, and if I understand what V is saying, they are describing the same person, maybe, or the same idea, or the same, I don't know, the same number, or whatever. On the other hand, if I write this thing, I will use a triple line for this. I will want to say that U and V actually mean the same thing. It doesn't happen that they are equal. They actually mean the same thing. Their intentions are the same. The algorithm maybe that they are describing are the same. It is what Frege calls as here where they have the same sense, and here they have the same reference. And Frege has a very nice example here. So I don't know if you are aware of like what's called the morning star. So the morning star is the last star that turns off in the morning. So like the night goes away, there is a final star there that exists with some light, and this is called the morning star. And there's also the evening star, which is the first star that turns on. Let's call it like that. And to say that they are equal is actually a very impressive thing. It means that we have made some kind of astronomical progress. We have observed something, because actually it turns out that they are the same. And actually they are not even a star. It's the planet Venus, Aphrodite. So we have these equalities here. On the other hand, I would not write that these things mean the same thing, and also Venus would not mean the same thing as morning star. So it is a bit tricky if we think that in any phrase we say we can substitute equals for equals, because I could say something like, okay, I don't know when this happened, like at this point, this guy discovered that Venus is the evening star, and this makes sense. But if we say that I can substitute equals for equals, I will end up saying, at this point, this guy discovered that Venus is Venus. It's completely trivial, and should make us start to appreciate that these two concepts are different. Usually, mathematicians will not care which of the two is being referred to, but this can lead to some, usually doesn't lead to problems. But when you start paying attention to how you define things, you need to understand what is what, because this is something that requires proof. This is a proposition. Okay, I don't get to say that two things are equal. Like if I claim that two things are equal, someone has the right to say why. Here, I'm just saying that they mean the same thing. Okay, maybe some person will say why, but it's a different kind of why. It's like a linguistic why, or it has to do with semantics or what we mean by these phrases. Another example would be, you just told me who is the head of the department, I forgot here. Who is the head of the department? Emmanuel. Okay. So somebody would say, let's say we're talking about now, that Emmanuel is the head of the department, I don't know. Okay, and in this case, I would say maybe why, or I don't believe you, prove it, and I will check something, and I will find out probably that you're right, and indeed this person is the head of the department. But definitely, being the head of the department does not mean being Emmanuel. Okay, so those things are distinct. Okay, so I will get back to this. I will use this notation that the triple bar will mean I'm talking about intension here, so it's not a proposition. Two bars means it's a proposition, it means something, and therefore it can be proven, refuted, believed, or whatever. And I will extend this notation, this is not so usual, to this symbol. So I have a proposition P and a proposition Q. This means that this is what's called a logical equivalence. It's like short for if and only if, or stuff like that. And I want to differentiate this from this. If I write it like that, this means that the two things I have written down are just the same proposition written in different words. They mean the same thing. So are we okay with this distinction? Okay, I don't think we're okay with this distinction because it takes some time to appreciate it, but at least I want to give it a name and a symbol because this helps the process of understanding what's behind it. Similarly, I will decorate this symbol with this def if there is a definition that's being happening, I don't know how to say it, being executed, being established. And the same thing with this triple bar. So for example, I would write this thing. A divides, let's say, B. I will make a definition, and I will define it as something like, okay, there is a K such that A, K equals B. I might write something like that. I mean, you should have seen something similar probably in like a number theory course or in basic algebra or I don't know where. So what's the difference if I write this versus if I write this? Here, this thing is a definition. I'm defining something. The idea is that before you read this line, this was meaningless. I'm just inventing a symbol here and I'm giving it a meaning, and the idea is that you know what the right-hand side means. And from now on, this thing will be just an abbreviation of this. So it would never make sense after this line to say prove, like, I will try to pick this, like, if I ask you to prove this, it will be rather meaningless. Like, I mean, it will be rather trivial because these things mean exactly the same thing. On the other hand, if I say prove this, prove that this thing mean the same thing. It's just a matter of looking at the definition, and definitely I cannot ask you to do this. Prove that this is defined like that. It doesn't make any sense, okay? And similarly, he will never reason in mathematics saying, okay, suppose that these things are equal by definition. Because being equal by definition is not a proposition, okay? It's what we call, okay, another buzzword here, it's what we call a judgment. So another difference that we want to establish is proposition versus judgment. And this is an example of judgment, and this is an example of proposition. Again, this is not supposed to make total sense right now. Throughout this semester, I hope it will start making some sense. Any questions? Yeah. It can be in either English or Greek, it doesn't matter. Okay.
So when you say a judgment, is that like a statement that can take a truth value, like, or is that what you're trying to say?
Okay, thank you very much for this question. If it's something that can take a truth value, I have not mentioned truth values yet, and this is quite, it's a nice opportunity to go there right now. Okay, I will open a big parenthesis. In case you're still with the same question, by the time I close it, ask it again. So, like you are in school, you are doing your first proofs, probably Euclidean and geometry or something like that, and you start to prove things and appreciate what it means to define something and what it means to prove something. Then you get something like a logic or half logic course or something like that, and you start talking about booleans or like truth values or something like that. And then you start interpreting like the so-called connectives, which you may have seen or not, but I will start writing them here. It's a good opportunity. So we have like a symbol for the conjunction. I can use either this or that. Disjunction, I will write it like that. I have implication, I will write it like this. Or, I didn't like it. Like this, or like this. I have negation of something, and you have the quantifiers. And then what? You have also equation. Equality. Okay, how many are these? These are 7. And this will be pretty much the only. I'm lying, but it's on purpose. I will lie sometimes, okay? And like most of the times it's on purpose, and most of the times we will discover the truth later on. So there will be like these 7 things, and you study something called truth tables. And then you keep wondering, I hope, that what truth tables have to do with proofs. It seems like a completely different thing. It seems like just algebra, a particular kind of algebra on a set with like 2 values, and the operations are not the usual ones. They are like conjunction, disjunction, maybe what you would be led to believe that it's negation, or things like that. So we have this idea of booleans, and I will, what's your name, sorry? Manolis. Okay, so I will take this opportunity by Manolis' question, and I will write one more thing here, which is like the difference between boolean and propositions, which is huge. And this is one of those things that usually takes a bit to get to appreciate it, and then you have the aha moment, and you completely see the difference, and you cannot believe that all this time you were struggling to understand that these things are 2 different concepts. So we have the booleans and propositions. I will write it like that. And so I could say that propositions are meaningful statements. They definitely have a verb. In this, there's a verb like 5, I don't know, is an even number. This is a meaningful statement. I don't care if it's valid or not, okay? But it's if I say it, it means something. And it makes sense for someone to say, I believe that, and followed by my proposition. Or, I know that, blah, blah, or I will prove that, blah, blah. These are like tricks up your sleeve that you can use to decide if something is a proposition or not. On the other hand, the judgments are on a different level, and they seem to be something like, I have decided that, blah, blah. And a typing judgment that I will write like this, we will use the 2 points to say that something is of type something. So if I write like something like minus 42, two points, like, I don't know, int for integer, you might say, wait, there's a verb here, because you're saying that minus 42 is an integer. And this is not at all what I'm saying. And a way to defend my trick, that if you can say, I believe that, blah, 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 then it's a proposition, otherwise a judgment, you could think of this like the integer minus 42. And now there's no verb there, and there's no confusion. And it doesn't make sense to say, if the integer minus 42, then something. Where's the verb? On the other hand, if I write something like this, minus 42 belongs to the set of integers, this is a proposition, and you can say, I think that minus 42 belongs to the set, or I will prove that minus 42 belongs to the set, and all these things. So this is an example of a proposition. It makes sense to doubt it, to believe it, to prove it. You could attribute a truth value to it. If you think like in truth values, I will try to avoid this. But you cannot do this here. It doesn't make sense to say what is the truth value of this. This is like something on a different level. And the reaction of Manolis, which is like a bit shaking his head like that, is the perfect reaction to have at this point. So eventually we'll have this aha moment, and you will realize that these things have nothing to do with each other. Yes, sorry.
But what stops you from writing minus 42.1 colon integer?
Exactly.
Okay, this thing? Okay, so each type, this is like maybe a question for a bit, but I will just give a bit of I don't know, a preview or a teaser. So each type will come with certain rules of how you can construct its elements, and actually for each like typing statement you have there, if I want to say that this indeed has this type, I will have to make a construction which will be mechanically checked. I think it's better if I do this with an example. Like when we start playing with types, we will see the difference between what it means like to prove a statement or to infer a type. This would be like a type inference for something. Like I will give a different example which might be better or not, I'm not sure. Like if you have that x is an integer and y is an integer, you want to be able to infer, and this is it's the first time I'm using this line. Probably a lot of you have never seen this line. It means I'm inferring what's below from all those things that are above it. I was not planning to do this right now, but it's okay. X plus y is an integer, and this will be like, you could think that this is a proof. In a certain sense, I'm proving something. I'm proving that this actually is an element, is of type int, but the proof that I will do about integers will be on a different level. What did you want to say, or? Αν δει. Αν επιτρέπεται. Ότι επιτρέπεται. Okay, let's say it like that. If you write this, the actual foundations or whatever you have behind it will complain. It will not be a matter of arguing within it to try to see if you will prove it or not. It will be similar if you've seen like a programming language with types. Static is redundant here. You either have types, plural, and they are static, or you have only one type, and people call this dynamic types. But okay, this depends actually on the system you're using. So for example, some systems will say, if you write this, I will make it easier for you. I think you meant to say minus 42, and I will forget the point 1. Whether this is a good idea or a bad idea is up for debate. Some system will say, oh, I don't know, this is not a valid, they have a syntax error, let's say, like that. So for the time being, I think the best I can say, we will come back to it, is like it's a problem or an error on a different level than if I say minus 42.1 belongs to the set of integers. This thing I can refute it. First of all, if I put it on my table to prove it or refute it, it means that this is something on my table and it has chances to be inside this set. So, okay, I will open a new parenthesis. We're still, I think, on your parenthesis, right? Okay. Okay, it's a good moment. Remember when I said that I will lie sometimes? So yeah, I lied a bit here. So I said that I will write U equals V. There is something invisible here in this equality, and it's a decoration that I will write it as alpha, where alpha is like some type. So I don't really have one equation, one relation called, sorry, I keep saying equation, it's wrong, it's equality. I don't have a universal equality in my world, exactly because I don't live in a world where there is only one kind of object. There are types which classify all objects of interest, and so for each type, I have the idea of equality within this type. And the same goes for this thing, for this symbol. Surprisingly. So if I will decorate this with an alpha, and so if I write like something silly like Thanos, and here let's say G is the set of all people who were born in Greece. This is a meaningful statement. Whether, actually, if I replace this with this, it's not that I can prove it or that I can disprove it. It's not false. It's much worse than being false. It's meaningless. It has a type error, as we say. I cannot even say it and expect some. It's as good as if I write something like, I don't know, exists some integral sign minus Thanos equals. So this thing is pretty much as meaningful as this thing I wrote. Okay, so I will. So the idea is that in order for this thing to make sense, the type of this guy, okay, let's start talking about types, must be person. And I want some suggestion on what the type of this guy must be. Yeah, okay. Now, actually, right now, the idea is that, I'm sorry, I should have removed this. Okay. Yeah, okay, now, so I'm trying to do my first probably type inference here. And the question is, what type am I expecting to see here by the context I have written around me? So I have written something here, which I know is a person. Here I have written this symbol. And I have not told you what the type of the symbol is, but I hope you can infer what the expected type of this thing on the right should be. Yeah?
Set of people?
Yes. So I will write this like this, set person. So we are discovering also that there will be no type called set. It will always be set of something. So this is already a difference, because in set theory you would be perfectly fine with this set, while we cannot find a type to put here, a certain alpha, that this will be a set of this type. It's neither a set of type person, it's not a set of integer, it's heterogeneous, sometimes it's called like that. So if I want to generalize this, here I must have something of type alpha, and here I must have something of type set of alpha. Okay, I'm saying set of alpha, and I haven't mentioned this, but almost always in this class we will denote application invisibly, actually a bit visibly, because I will always leave a space here. So there is some a little space here, the way I wrote it, and this space does something. It's how we will denote function application. Okay, so I noticed now that I'm supposed to have a break, and we're supposed to take a 15-minute break and then come back and stuff like that. Since it's the first class, let's do that. But was the surprise I was referring earlier. Maybe some is a heavy smoker and cannot stand like 90 minutes without that. So I expect by Friday to quit smoking or something like that. Let's try to do 90 minutes all together, like consecutive, and we'll see if we can shift it in the beginning of the 2 hours that we have, or in the end, or in the middle. We'll resolve this through Zuli because it's a meta subject, not an actual subject. So let's take a break for like 10 minutes, and then we come back. Okay, so this is why I don't want to have breaks, actually, because I have no idea what I was saying. And probably, I don't know, can somebody help me? I know what I wrote down here. Okay, so remind me your name. Yes. Sotiris, you just asked something about? Types. Okay, yeah, so what's the deal with, pretty much Sotiris' question. No, he had a deeper question, like what's up with types? Okay, so pretty much the question is this. Okay, we are starting to appreciate very superficially that these things are kind of different. Okay, so like it's not the same thing if I write A has the type alpha, and it's not the same thing if I write something like A belongs to some set A. At least I will use them as different things. The crucial difference is that this is a judgment, while this is a proposition. And as I said, in order for this to be a proposition, it means that this comes with its type, this comes with a proper type, and there is a hidden type here as well. Okay, but to come like what's up with types, the idea is that we want to classify all objects of interest, and we will not have a finite amount of types. It's like an open-ended world. You may feel the necessity to say something like, I want to define a new type. Okay, so go ahead and define a new type, and we'll see how we can do it. Pretty much we have to say what it means to construct an element of this type, what I need in order to construct my actual type, and how I can use elements of this type. So this is the approach that comes here. And the same ideas, as I said, will have a corresponding part here and a corresponding part here. So this will make sense once we start actually talking about type inference and typing rules and typing systems. For the time being, it's natural. It's a very natural question of what's the difference between a type and a set, because in a certain sense they seem synonymous. But I'm just alerting from the first class already that they are not even comparable, these two statements. They are they live in different worlds. Examples of types will be like, I think actually this is a good time to start writing some statements. Okay, so let's say, I'm being very egocentric here. No, I will not be. You said that your name is Sotiris. Okay, so Sotiris, should I write it in Greek or in, I don't know. Let's keep it supposedly English. Sotiris is of type, I presume, person. So if the whole thing I wrote here is like a typing judgment, or a typing maybe. On the left I have some object, on the right I have some type, and I'm saying that actually this thing comes labeled by our understanding as something of type person. And now if I say something like, okay, I will come back to myself now, or almost. If I say something like mother of Thanos, and I will write my name in Greek, okay. What do you suppose the type of this thing is? Okay, person, okay. On the other hand, if I write, we can start having some fights already. What about 42? What's the type of 42? It's an answer. Yeah. It's let's say I can write int here to say that it's an integer. Somebody may say, wait, it's actually a natural number. Or somebody else might say, actually, no, it's a real number. Or a rat. Rats are the rational numbers, obviously. Which of us is correct? And this has to do with the question of Manolis. It's not really up to debate. Each person is referring to a different thing, and they are all right. We just have a clash of symbols, of names, unfortunately, because all these 42s here are actually different. And the idea is that the context always helps us understand if I'm talking about the integer 42, the natural number 42, the real number 42, or the rational number 42, or the whatever number 42 I may have in mind. So you could think like that maybe we should be decorating these things with something like, I don't know, int, not, but we never do that, although they are different things. So just a second. So I told you I will tell you many lies, but this is a lie I never told you. But you've been told this thing, like this set is a subset. I haven't said what subset means, but I'm counting on your studies so far, of the integers, which is a subset of the rational numbers, which is the subset of, I don't know, maybe the algebraic numbers, which is a subset of the reals, which is a subset of complex numbers or whatever. So I'm not saying that this is false. I'm saying that this is worse than false, in the sense that it doesn't even make sense, because I'm comparing sets to be a subset of a different set. You should first of all be sets of the same kind of things. And here, the inhabitants of this type are natural numbers, nuts, I don't know how you want to call them. Here are different kind of things, integers. So what actually happens, and we can abuse a bit our mind, our notation, and get away with it, but what actually happens is that I have some inclusions here, like inclusions in the sense of ways to embed each set on the left-hand side to the following set, and maybe with the comforts or the conventions we have, we get away with it, saying that, claiming that 42, the natural number, I don't know, belongs here to the set of integers, but this is actually completely meaningless. If my system or my colleague when I say system, it can be a human being, okay, don't necessarily think of a machine, accepts this, probably what happens is one of the many aspects of what is called invisible mathematics that takes place and we don't even realize it, and we don't really appreciate it unless we start to put things on the table and start to reason formally. And here what's happened is like a type coercion. I have, you may know this from programming languages, it's the same reason that like a language might accept 4, the integer 4, when it appears in a context where your language wants to see a floating point number or something like that. It will typecast this thing into the broader context. Pretty much this function will do all the work I need to do and will translate this, and if this happens invisibly, I will never realize that this is meaningless. Okay, so it pays off to start paying attention to these invisible things, and we'll have to do it if we want to understand how proof assistants work, and when you want to do foundations of formalization, I mean, it's something you need to pay close attention to. Somebody asked me something, and I started this new parenthesis, but I don't remember what the question was. Is it okay? Can I go on? Oh, yes. What's your name? Aretis, yes. Okay, so what's the point of having two different 42s, pretty much? So the idea is that each type comes equipped with all the notions that we care about this type. Like we can add things in the integers, we have subtraction, we have multiplication, stuff like that. And we consider that this is the world of the integers. Natural numbers, someone might say it's a completely different beast. And even though you can find a representation of the whole natural numbers within the integers, it doesn't make sense to say that they are the same thing. What is valid is that if you only like integers, let's say, and somebody tries to convince you that I have some very interesting type here, a set of numbers called the natural numbers, you could say, okay, I found a subset within my universe, within my integers, and I can do pretty much everything you do, and there is a translation that goes back and forth. So when you do something with your natural numbers, I just want to make sure that I can translate it, your 42 over there, I can translate it to my 42, which is an integer. And if this translation behaves well with the operations that we have, you have convinced me that your subset can play the roles of, is like, just to reuse the word I was saying, an implementation of the specification of natural numbers. So I can say directly, my natural numbers satisfy these things, and then you say, I can find a subset with these things that satisfies this, or you can create your own, like that's fine, as long as we have these two translations. So for the time being, it's like, it has a different purpose, it has a different meaning, it's a different thing. Like it's, I like your reaction as well. It's similar to Manolis earlier. We will have a lot of shaking heads like that. Like, I kind of get what you mean, but it's not convincing so far. And the idea is that it will become convincing by using these things, I hope. Yes, Sotiris.
Yes. So we say that the natural numbers inside the integers is an object that has the same sense as the natural numbers, but it's not equal to them.
Actually, it doesn't have. It's neither the same sense nor the same reference. It's okay. We can use a notation for that. Like, I have not decided which of the two are better. I mean, you can help me with that. I would like to say something like this: the set of all x's of type int, let's say, such that let's say x is greater or equal to 0. You might say, okay, we will not get into a discussion about 0, if it sounds nice to be a natural number or not. For us, I will consider the idea of 0 to be natural. If you don't, we'll have to invent a new name for the numbers 1, 2, 3. The counting numbers, as I said. For me, the natural thing to say about natural numbers is that they represent the size of finite sets. And I consider the empty set to be finite, so I would like to apply the name natural to 0 because it represents the cardinality of the empty set. But let's not get into this. You could see something like that. Let's say I want to define n to be like this. I would like to change the notation here and either use something like these guys or this. I don't know which makes more sense. But the idea is that these are the natural integers. And similarly, I will have like, these are the natural reals. Which are the natural? Yes, take all the real numbers that you know and pick 0, 1, 2, 3, the real ones, and these are the natural reals. And now I can say that the natural reals indeed is a subset of the reals. This is a meaningful statement because in both sides I have sets of real numbers. But I wouldn't like to write this. Like, people who write this are bad people. Okay? No, it's not like that. People who write this, actually, when they use that, they mean this. And usually, for some reason, they consider that like numbers are actually the real numbers, and let's focus on certain subsets. And this is quite interesting. When you are taught calculus, which is the theory of real numbers, it's just the nickname of the theory of real numbers is called calculus. And when you study the approach usually is, we suppose that we have some things called real numbers, and we suppose that we have like this axiom, like 13 axioms or whatever, that hold here, and let's see what we can prove from these theorems. I hope that this is the way calculus is taught here still. Is it like that, more or less? Yes? Calculus 1, like απλουστικός λογισμός 1. It has like a bunch of axioms, right? And let's suppose that natural number exists. We don't care about foundations. And let's assume these axioms. And it doesn't make sense to say, I don't believe these things. It's okay, fine if you don't believe them, but if these axioms are valid, let's see what we can prove. And all this theory is called the theory of the real numbers, or if you are friends with it, just calculus, okay? So, but when you study like the theory of numbers, which is a nickname, unfortunately, for the theory of integral numbers, right? Theory of integers, usually that's not the approach you take. I mean, has everyone taken a number theory course? Was it like that? Let's assume that there's something called numbers. These are the axioms of the integers. Usually it's not like that. Okay, I don't know why. I think it's like a social thing or a cultural thing, but I think it should be like that. And usually when I teach this, I teach it in the same aspects. Like we settle down on certain axioms and we start seeing what we can prove. But so to come back to it, when people write this thing, what they really mean is that a certain subset of the real numbers is a subset of the real numbers, okay? Which doesn't make much sense, okay? Yes?
I feel like having a specific symbol for the natural numbers and considering them a different entity is maybe useful in the same sense that talking about Peano's axioms and then saying that, okay, if we define the natural numbers in von Neumann's way, then they satisfy Peano's axioms.
Okay, this brings the idea of specification again on the table. So the idea is, Manuel is saying, if you have seen it like the Peano axioms, this is like a specification. If I'm looking for things that have this, I have this data that satisfies these rules. Can you find something like that? Okay. And there comes, let's say, von Neumann and say, yeah, I can find that within some set theory, and I can define there these guys, and I have the obligation to prove that my definitions satisfy the specification, and the moment I do it, I say that, aha, I have an implementation of Peano's specification. So there is implementation of von Neumann, there is a specification of Zermelo, and there are various specifications. Sorry, I said specification, I meant implementation. So there is one specification of Peano, and there's some, like you can think of Zermelo, like trying to sell his thing. Say, okay, I have an implementation of this thing, would you buy it? And then comes von Neumann, say, I also have an implementation, and it makes some sense to say, let's see which implementation works better for my purposes. Maybe one is more efficient for what I want to do. But you should always work in an implementation agnostic way, which means that if you want to do something that anybody who is interested in Peano's axiom will take profit from this, use only what the specification says that must exist, and don't get into the detail, the implementation details, because you will start proving things that only work for your implementation. You don't have the right to say that I'm studying number theory, I'm studying Peano's things. You're just studying your implementation. And it's a pity if you do it without realizing it. But because maybe, I mean, if you have good mathematical habits, you will end up doing it either way. So like, pretty much no mathematician would ever ask this question, like if 2, I hope, belongs to the ordered pair 2, 1. Mathematicians should say that this is not a meaningful question. However, if you ask your foundations, and if your foundations happen to be set theory, they will say, okay, well, this is a perfectly valid statement, because on the left hand I have what type of thing? Trick question?
It's a set.
It's a set. It's the only type I have. It's a set. And on the right I have what type of thing? It's a set. Okay, so it makes sense to ask if this set is a member of that set. And although your heart tells you you should never ask this, and for the same reason you should never ask if the function of cosine belongs to the square root of 2. Yeah, it sounds like silly and funny, but and like a mathematician say, I would never do that. But on the other hand, it's a meaningful statement, because these are sets, and so that your foundations permits you to ask that. And if you like take some mathematical hygiene seriously, you will say, I will take care, and even though I'm using set theory, I will not ask silly questions, I promise, or something like that. On the other hand, your heart dismisses this, your mathematical heart. I'm trying to convince you pretty much that in your hearts you are already like type-theoretic mathematicians and not set-theoretic. I mean, you say you do set theory-based mathematics, but if you see what you write, it doesn't look like it. Okay. Okay. So why this is a meaningful statement? Okay, and if it's a meaningful statement, what's the answer? And you have to go back, like in page, I don't know, 12, where somebody defined this, and maybe you will see something terrible, like saying, I define this to mean this. And there are like various famous constructions for ordered pairs. So one of the more famous ones is the Kuratowski pair, which will end up being this. And okay, we already have some kind of philosophical issue here. I mean, I would like to have like not an analytic approach here, but a synthetic one. Aha, opportunity. I will always do that. Analytic, synthetic. Ignore me. Okay, so no, sub-parenthesis. The difference, when I say analytic and synthetic here, it's like think of analytic geometry versus Euclidean geometry. So lines and points are like atomic notions, primitive notions for Euclid, and it doesn't make sense to say that the line is a set of points or something like that. On the other hand, in analytic geometry, you define these things in terms of other things. So this is like a good example to keep in mind of this difference when I say analytic versus synthetic. So here I have like this thing. So if I define it like that, I'm using Kuratowski's implementation of the idea of the specification of an ordered pair. Now I can check whether this thing is valid or not, and it happens that it's not valid. Okay, so and I don't even know, right? Because somebody can spot this. What I just said is actually wrong. I say that if I use this implementation, this one, then indeed I can say that 2 does not belong to this thing. Am I right or am I wrong?
You're right.
I'm wrong. Yeah, this is the catch question. I'm wrong because I didn't look further down the hill. What's the definition of 2? Okay, maybe in some sense, 2 was defined, was implemented in whatever way to be this guy. Okay, or maybe not. And the point is what? This is all silly, right? I mean, you never ask those things. You take care to ask meaningful questions, but the idea is it would be a nice, like a safety net if your system doesn't even allow you to ask silly questions. Okay, like you have a steering wheel in your car and you say, it doesn't need to have a stopping point. I will never turn it backwards like that, but okay, it's better if your car doesn't allow you to do that in the first place. Okay, so I don't know, I opened a lot of parentheses, I always do that, and some sub-parentheses and stuff like that. Can I go back to writing some more interesting examples here, or,
maybe in set theory at least you cannot define 2 to be the 2.1 because you do not allow for sets to be included in themselves.
No, actually, you said I would have like not necessarily. Depends on which set theory I am. So there are various versions of set theory, and some permit this. You have some set theories that like satisfy the anti-foundation thing, permit sets that belong to themselves and are quite interesting. But this thing that you mentioned is not relevant here because I'm not asking if 2 belongs to 1, 2. If I'm working on Zermelo-Frankel, one of the axioms, the foundation axiom, will say that this is not true and I'm satisfied. But the question was if it belongs to this. The first question was if it belongs to this, and the second question was if it's equal to that.
I think he was talking about your definition of there.
Where? What?
Under the definition of 2, the possible definition.
This thing?
Yeah.
Okay. So about this one. Okay, thank you. It could be valid depending on what my axioms of set theory are. If they permit sets that can belong to themselves. Let's say like that. Okay, but I could have like a similar problem. So the point is, mathematicians tend not to ask these silly questions, even though they are claiming that they are using foundations that all these things make sense. So like, either when I write something like that, don't laugh at it, right? be honest and say, yeah, of course, a meaningful statement, and then you will you start becoming implementation specific, and you no longer get to say, I'm studying order pairs. You are studying Kuratowski's implementation of order pairs. Okay. So, yeah.
Τιμολογικά για ποιο λόγο λέγεται judgmental το σαν αριστερά, ενώ επειδή έχει να κάνει με την κρίση, ας πούμε, εξωγλωσσικά.
First of all, I would like a Greek word for judgment and judgmental. Krísi, maybe. Πώς? No, at least the categorium I have in my mind is a predicate, and it's a different thing. I don't know. No, okay. It's good. Probably, this is a philosophical thing, right? The idea of judgment and of extension and intention. I don't know if I should call them in Greek like ecstasy and ένταση.
Καταλαβαίνω ότι δεν ήταν αυτή η ερώτηση μου παρά.
Okay, yeah. You say, why is it called judgment? I don't remember who coined the term in the first place. I don't think it was Martin Lev. Martin Lev paid a lot of attention to this, but I think the term is earlier, but we can look it up.
Δεν είναι το θέμα μου ποιος.
Okay.
Ώστε να ρωτήσω, ποια είναι η λογική του πίσω.
Okay, we need a different word, right? To separate it from the idea of a proposition. And we have a propositional equality and judgmental equality, or maybe definitional equality. So, why choose this particular word? Let's call it some kind of synonym, and we want to distinguish. Like, you have group and set. Why call one group and one set? I don't know if this is a good answer. Like, you don't have a good reason. You just need to. You pick two synonyms. You say this will mean this thing here. No.
No.
Okay.
Σύνολο, εντάξει, διαστικά από το που περιγράφουμε, συλλογή συνόλων, η ομάδα έχει αντίστοιχο λόγο. Ρώτησα για ποιο λόγο λέγεται τέτοιο judgmental. Επειδή είπα ότι έχει να κάνει με το πόσο έχουμε ορίσει το τύπο, ότι είναι το in, το not, το real και το rat. Και σας λέω, okay, εντάξει, δεκτό, ότι έχει να κάνει με την κρίση του πώς έχεις δώσει την περιγραφή του τύπου. Όπως λέγεται judgment, ότι έχει να κάνει με την κρίση του αρρώστου, πώς θα ερμηνεύσει.
I think this is like a semantic linguistic point, and I'm really interested in this. I'm not saying that it's not important, it is, but I didn't really get why it's different from the group and set. No, I mean, I don't want to be. Okay, we can. Okay, it's kind of. It's not off topic. It's very on topic. We open a topic on Zulip. But you also said that you think there is a reason behind group being called a group and not a class or a set, and I think in all those cases, pretty much. Group? I don't know. For me, I mean, I think we think like that because we were trained to think like that. If you see someone who has never studied any math and say group and set, are they synonyms? We say, yeah. It's a group of people, a set of people. Okay. We take it on Zulip. So, any further questions? No. Okay. So, I would like to start giving some like more meaningful typing things here. I only have Sotiris and a bunch of numbers and my mom here for some reason. Okay. So, another thing I would like to say is like, okay, I will come back to like. Manolis was born in, okay, let's say Greece. Not necessarily this Manolis or whatever, but supposedly I know which Manolis I'm referring to. So, okay, quiz, what's the type of this thing that I wrote here? Okay, I will reverse this. Who would say that this is a proposition? Okay. Who would say that this is a judgment? Okay, nobody. Good. Who would say that this is a Boolean? Okay. We have some disorder there. Okay, fine. Okay, so the answer here is a proposition. The idea is that if I know where Manolis was born, I can, or to attribute like a truth value to it, which means I can have a mapping, a function or whatever, which takes this proposition and, or an association, I don't want to say function, between this proposition and say, okay, I will attribute this Boolean to this proposition depending on whether indeed Manolis was born in Greece. But in absolutely no way this will be a Boolean. There are only two Booleans, like true and false, and there is an infinitude of propositions, and definitely, supposing that Manolis was born in Greece, and supposing that 2 is prime, this should not be the same member prop. It's not the same proposition, okay? So if you think, unfortunately this is called classically, and if you are so influenced by this, we will get back to this mistake. As I said, Hilbert, one of the greatest mathematicians, huge mistake, misunderstood his own student. And pretty much if you see things like that, you end up saying that mathematics is just a huge amount of calculation in order to find out if what we wrote down is just the proposition trivially true or the proposition trivially false, and there are only two propositions in mathematics, true, one called true and the one called false. Obviously, it's not like that. So when you prove a theorem, it's not like all the theorems that are actually theorems, it's the same thing. Okay, they are valid, they have proofs, but we need to understand that the propositions are different, and this is why it makes sense, and it's a human activity to communicate mathematics, and it just does it. Let's do some calculations and find out if this ends up being true or false. So, having said that, I want to introduce, because we have enough time to introduce this, and it's extremely important, the concept of holes. And I will start inserting some holes here. Okay, so I will take this. I will take this out of. Okay, so I will take this thing, and I will erase Thanos, and I will put a hole here. And now the question is the same. I ask, what's the type of this thing? So what's the role of holes? The idea is that I'm waiting to receive something in order to become something. So this is like a function. So this phrase that I wrote here, you can think of it as like not being saturated yet. Still, it expects something. And the notation I will use for things that are expecting certain things in order to become certain things is just an arrow, where on the left-hand side of the arrow, I will write the type of the thing I'm expecting, and on the right-hand side of the arrow, I will write the type of the thing that I will become the moment I receive this input, okay? So, left-hand side of the arrow should be? Person. Easy question. Right-hand side of the arrow? Bull. So, this means, wait a minute, that you're saying that if I put here like a person, for example, Thanos, this becomes a Boolean. And my mother is neither true nor false. Okay? So you can cheat here. Yeah, you can cheat here. How can you cheat? See what it was. I started with this thing. So just check what it was and just copy-paste this person here. Opa, I did not copy-paste this properly. Okay. So maybe I should emphasize this, saying that like this person, sorry. Okay. I tried to do it quickly and I failed miserably, person. But what I'm trying to say here is like this person is like the same as this person. And that's why how you can cheat on my question. The green thing should go there. And the type of this thing, use a different color, like the type of this thing is what goes here. Okay? Does that make sense? Okay. Let's do some more like funny exercises. So what would happen? No, this will become like, I hope this will become like more interesting. Okay, so what happens here? Raise hands, please. I want some suggestions. Somebody who never spoke so far. Panos, go there, say it.
Country to prop.
Perfect, okay. Let's suppose that Greece is a country. I don't know what the definition of country is exactly, but okay, let's say it is. Country to prop, and how did we answer this? We cheated again, because we have access to this, okay? And I saw what was got abstracted here, it got wholeized, and it was something of type country, so I know that on the left-hand side I have country. And what the whole thing was, when it had all its things completed, it was a proposition, so like if you plug a country in here, this whole thing will become a proposition. Make sense? Yeah? Okay, great question. If you don't have access to this, okay, the idea is maybe it's this thing, I claim that this thing is almost enough, but somebody could argue I can give this type to this thing, but maybe I was being more specific. Maybe, I don't know, this was like a hospital, or it was like a city, or a continent, or I don't know what, okay? So indeed, there's certain ambiguity, but the idea here is that all these different answers, possible answers, are because this idea was born in where different was born in. Okay, one refers to being born in a country, the other blah blah. Okay, does that make some sense? Okay, so what happens if I say, I don't know, let's say Brazil here, why not? Notice that I don't care about the validity of these propositions. I only care that they are propositions. They are meaningful statements, regardless of whether I know if they are valid or not, and regardless of whether they are valid or not. Okay, so somebody who hasn't spoken so far, please help me here. Yes, and your name? Kostadine, go. Okay, if anyone wants to fight with Konstantinos, that's fine. And you should raise your hand and say, I object to it, I think that's something else. Okay? Yeah? Okay. Your name? No, okay, maybe I closed my eyes. It was I was referring to Vangelis? No, you, yes. Lazarus, yeah, exactly what I said. Yeah.
We place any living being?
Okay. But it's not like you object to it. It's like similar to the country, city, continent, hospital situation.
Something more generic.
Okay. And Areti, what was it? Was similar objection or different? Okay. Yeah, could be like a dog or something, a pet or a cat or whatever. So all these things are like, it means that you understood the idea of the context in a different way. Okay. So if I tell you, okay, but when I say this, I actually mean a person. It's not like who is right or who is wrong. It's pretty much similar to the idea of, am I referring to hospitals, countries, cities, continents, or something like that? Yes? Again, Lazarus?
Couldn't we talk about an idea?
Okay, yes, like democracy was born in Brazil. Okay, of course, okay. So it helps to know where you started and start abstracting things. And now, okay, any other? Okay, I think we get the idea of suggestions, but what? Oh yeah. Bornable, yeah. Anything that is bornable. Okay. I will consider all these answers like correct, and like they are not actually propositions, so we cannot say let's prove that this makes sense. It has to do with linguistics, with what we understand, with the semantics of these words. Okay, it's not a mathematical debate. It's a let's agree debate. Yes?
Έχουμε δει μέχρι τώρα τύπους που είναι κατηγορίες εντός εισαγωγικών αντικειμένων. Αυτό εδώ πέρα που είναι έτσι πρωτογενής χαρακτηριστικό, αυτό εδώ πέρα είναι κατάφραση που κάνουμε. Είναι όντως κάτι το οποίο επιτρέπουμε.
This thing here?
Ναι, το κομμάτι με τις τρύπες τέλος πάντων.
It will be super valid. It's not like temporary. We will use this thing.
Οπότε είχαμε τον τύπο και στα δεξιά σαν κάτι τελειωθάζουμε τύπους. Οπότε τώρα τι αυτό είναι τύπος συνάρτησης και καλά στα δεξιά.
This arrow here is to remind us of like a function. The idea is that it's something that takes these things and becomes these things.
Ακόμα είναι τύπος όμως.
What?
Ακόμα είναι τύπος.
So this thing, yeah, this is a type. Yeah, okay, so thank you. On the right-hand side of the two dots, whatever appears there, it's a type. So this is a type, and this is a type, and and this is a type, which was something like, let's say, person to prop, and this is a type as well. Yes. Okay. Last question, because I really want to say this next thing before we end the class. Yes.
Εφόσον μπορούμε να έχουμε περίπλοκους τύπους και όχι μόνο primitives. Πριν που είπαμε ότι το 12 και χάνω ως set, ότι δεν μπορεί να είναι set επειδή δεν είναι ενός μόνο τύπου. Δεν μπορούμε να ορίσουμε έναν τύπο που είναι πιο πάνω.
Okay, what I think Konstantinos is saying is like, couldn't we have a type that has integers and persons as well, something like that? We will see how we can deal with that later on. We definitely want to have some way of doing it, but a tidy way of doing it. It's not like in set theory that you take the union and you put everyone together. So we have to take some care there. So the great point is, you will doubt it right now, I think. At the same time, I want to convince you that this is a great idea and that actually it's nothing new, which is weird. Okay, I want suggestions here. And we already have some suggestions, but before we have suggestions, I need some kind of notation, because here I have like two holes, okay? And I need to have some conventions or some whatever. So the idea is that I want to capture the idea here that I have two arguments. So I want to have an idea to have types that can express this idea that I take something of this type and something of that type, and I take it like in a package or something like that. And now I want to hear suggestions. And okay, you never spoke so far. What's your name?
Asterios.
Asterios. Go on.
We can maybe have like something like a Cartesian product or
Okay,
carrying.
Okay. So you're way ahead of us here at this point. So if I'm looking at this thing, it looks like I abstracted two things simultaneously. Okay, so I need the correct types for each argument, and let's say that we have agreed that this is first and this is second. This is nowhere visible with my notation with holes. Already a drawback with holes, although they are very useful. So Asterios might say, the first suggestion he's offering here is like that this is, give me a pair, and I will denote pairs like that, the collection, the type of pairs like that, person, country, and I will become a proposition, and I need parentheses here because we haven't established rules of precedence, so I will use this parenthesis here. So this is how I would visualize it if I understand that I had a statement and I abstracted two things simultaneously. One was of type person, the other was of type country. But let's say I didn't tell you that I was looking at this one, I told you I was looking at this thing. You will agree that if I abstract Manolis, I will get this. So I just need to run with this, or withhold your objection maybe. Okay, so in this case, okay, tell me the answer.
Είναι συνάρτηση, ξεκινάμε από το country και πηγαίνουμε σε μια συνάρτηση τύπου person σε proposition.
What was your first one? Country or person? Okay, good answer. So I want to abstract this thing. So by cheating, I know that if I receive the proper argument, I will become this thing. So this will be like, I'm cheating here, country. And on the left-hand side, I abstracted the person. However, I could visualize it the other way around, like I have this thing, and I abstract the idea of Brazil, the object Brazil here. So in this case, it would be like country. And in this case, I will become like the whole thing becomes person to prop. So we are pretty much out of time.
Please explain the second, what you wrote.
Okay, this thing?
Yes.
Or this thing? Or either?
No, the last one.
The last one? Okay, so you're fine with this one?
Yes.
And you're not fine with this one?
Yes.
Please explain why.
Because it looks as if the first argument that you're going to put is a country.
Okay, so when I was looking at this thing and I said I will abstract these two guys, the first argument will be this and this, there was no objection, it's like that. If I told you that I abstract them in the opposite thing, you would just swap these two, right? But now, in this case, I am looking at this thing, so if I abstract something from this thing and then plug it in, I should get this type. So this is why I have this type. Did I mess the order?
Okay.
No, sorry. First was this, right? So I will get, it's correct here. I will get this type. While on this example, I start with this thing, so I know that if I abstract further something from it, it will become this, and this is what I wrote down. And what is the thing that I abstracted? It's this thing. Okay? So this is called the idea, I will end the class with this observation, the idea that these guys are, as we say, like maybe isomorphic or something, is a very profound and advanced idea. I'm being very sarcastic because I want to claim that actually you learned this in elementary school, but it was in disguise. Can anybody guess what I'm referring to from elementary school? I don't want first semester, I want elementary school. Yes? No, it's not associativity because it's a different operation here. I think I will leave you to think about it. It's not so obvious. Everybody saw this in elementary school? Maybe proteinasio, I don't remember well, but it's like that kind of level of math, this idea, but with other clothes, like in disguise. And I think we end the class here and we shift all meta stuff and non-meta stuff in Zulip so that we have something to talk about until next class, which is on Friday. Either way, yeah. So the thing, of course, yeah. So the thing you said, I'm really interested in the thing you said about groups, and I want to discuss it in Zulip so that everybody can take place in this.